Hi, everyone. So good morning, good afternoon, and good evening, depending on the time zones that are you in. We're extremely glad to welcome all of you to the second talk of the monthly colloquium series by Carinas. We are very delighted to have Professor Preeti Kharb as our today's colloquium speaker. Well, before getting started with the talk, I will say a few words about this forum, Carinas. Carinas currently has more than 300 Indian researchers working in astrophysics and related fields, with 41% within India and 46% who are currently studying or working in abroad. And 87% of our members are early career researchers who are in the formative stages of their careers. These are the stages in which we start losing women researchers from academia due to various reasons. So this forum's goal is to empower these early career women researchers in India and first generation Indian women researchers outside the country through networking, support, mentorship, knowledge sharing, and collaboration whenever it is required. We aim to address gender inequity in a bottom-up approach and create a safe space, friendly and inclusive environment, and collaborate with other national or international organizations to amplify our impact. Among our initiatives towards reaching these goals, we have started a newsletter series where we not only focus on the great sciences done by women researchers, but also their life experiences in academia. For example, our first newsletter captures the experience of 3 generations of women astronomers. And the next edition is going to launch in February with some very exciting content, so stay tuned. And also check out our website, carinas.co.in for all of these updates. Our next initiative is this monthly colloquium series where we already have our first talk by Professor Annapurni Subramaniam. Now the time for the second one. So with no further delay, I'll pass on the virtual mic to Namrata to introduce today's speaker.
Thank you so much, Monami. So today we have Professor Preeti Kharb. So Preeti is currently an associate professor at the National Center for Radio Astrophysics in CRA, which is a branch of the Tata Institute for Fundamental Research, TIFR, located at Pune. Prior to NCRA, Preeti was a faculty member at the Indian Institute for Astrophysics in Bangalore. Preeti completed her PhD on a study of active galactic nuclei from IIA in 2005. Subsequently, she did her postdoc at the Rochester Institute for Technology, RIT, in Rochester, New York, where she worked with Professor Steffi Baum and Chris Odia, who were experts in radio AGN, as well as at Purdue University in West Lafayette, where she worked with Matthew Lister with the Mojave program. Preeti was one of the original proponents for the creation of the Working Group for Gender Equity of the Astronomical Society of India, which was formally approved by the ASI in 2015. So I think Preeti is a perfect colloquium speaker for our Karina's program, and I'm so happy to have Preeti as our speaker today. So yeah, Preeti, take the floor. It's all yours, and we will. And we also wanted to ask you if you want to take questions in the middle of the talk or towards the end. Do you prefer it towards the end? Or if you just want people to interrupt you?
Yeah, I think towards the end it'll be better. And then I think we can, yeah.
Okay, sounds good. All right. Thank you so much. And take it away.
Sure. Thank you, Namrata, and thank you, Manami. This is fantastic. It's a great honor to be the second speaker in Karina's. I congratulate you all for the creation of this, and I really hope there will be a significant impact in the long run. So with that, let me start by talking on about low-luminosity AGN. So that's my field of work, and I hope I will be able to convey the idea to you that even though these are low luminosity AGN, they are the majority of active galactic nuclei, and therefore studying their impact is significant for understanding of our universe. So let me begin with some introduction of an active galactic nucleus. So AGN. So this was the work kind of got a kickstart in 1940s. And this was through the work of Carl Seifert. So Carl Seifert was basically examining the optical UV spectra of some spiral galaxies. And that is when he found that there was a small fraction of spiral galaxies which seemed to be slightly different from the vast majority. And so that is kind of highlighted with this image. So on the left panel, you have a face-on spiral galaxy, which is, of course, you can see a lot of stars. Of course, you can't individually resolve the stars. You can see this fuzz of light from the stars. And then you see that the center part of that galaxy is bright. And that's because the stellar density towards the center is increasing. So there is a bright center there. And you see dust lanes, you see in this image. And some of the stars, bright stars, may actually be either part of that galaxy or even our own Milky Way galaxy. On the right side, you see another spiral galaxy, which is also face-on, which shows similarly everything that you see in a spiral galaxy. But on top of that, you see a star-like nucleus, which is superimposed on the center of this galaxy. And now we understand that this is what is an active galactic nucleus. At that time, of course, it wasn't clear. What was very interesting, very soon it was realized that this star-like nucleus was so luminous that if you, for example, the luminosity of the star-like nucleus could be 100 times brighter than the luminosity of the entire galaxy. And so initially, several of these galaxies which were found, if you took short exposures, you only saw the star. So that is how the name of quasi-stellar objects, etc., came about. So this is the start of the work on active galactic nuclei. The second thing Carl Seifert recognized was that the spectra of these galaxies was different. So the spectra of the normal galaxies, spirals, ellipticals, etc., are dominated by absorption lines, as you can see here. And these absorption lines are from the stars, the photospheres of stars that make up this galaxy. On the other hand, you have a spectra of an active galactic nucleus, which is dominated by emission lines, as you can see here. And there is a whole variety of a variety of species, a variety of shapes. So you have narrow lines, and then you have broad lines, and on top of them, there is a narrow line feature, etc. So these two characteristics, which is a star-like nucleus and emission line spectra, became the two characteristic natures of an active galactic nuclei. It was 20 years later that the first high redshift AGN was discovered, and that was the work of Martin Schmidt. So what they found was this spectrum, which is shown here. It is from their study, where they were able to identify what looked like Balmer lines of hydrogen, but they seem to be very, very at different wavelengths compared to what you see them in the lab. And that it took a while to realize that that was actually an active galactic nucleus at a high redshift. That was the highest at that point, was 0.158. Now we have redshift 6 and 10 and everything, especially with the James Webb Space Telescope. So it's completely revolutionized our understanding of the universe. But that at that point, 0.158 was the highest redshift object. And now we know redshift is, this is how the redshift is defined. At the same time, in the same year, in fact, it was also identified that there was a radio source associated with this object. And so that is where kind of the study of active galactic nuclei really started in in its fullness. Once the radio telescope started making very stable images, the whole field of AGN then became, of course, a very, very interesting field to kind of pursue. So on the right side, you see now what is a much better radio image of this quasar called 3C273. So 3C is the third Cambridge catalog. This is a radio catalog. And so that 273 is a 273rd entry from this catalog. So now you have a much better image of this quasar. When it was in 1963, what was found was only this bright point source, which happens to be the center of the quasar, and this hotspot here. So these were the two things that were found initially, but now we have the whole jet in its glory. And the bottom, what you see is what also kind of, highlights the point which I made, was that if you look at the source with maybe a If they're very luminous, even a long exposure just reveals a star-like object. This is the same object, 3C273, with the HST, the Hubble Space Telescope. And you just see a bright point source. You don't see anything else. But if you can somehow hide this bright point source, which was done here by some kind of occultation with the disk, then you see the host galaxy showing up. So this is how the field started, and as you know that I mean, now with the advent of the Event Horizon Telescope, I mean, this has completely taken off, and we are kind of living in very interesting times when it comes to AGN studies. So after the radio images became routine, it was found that most of the galaxies were of this type. So that means this is what is now called a radio quiet AGN. So you have the host galaxy here in green. You see the starlight in green here, green emission. And the red here is hot X-ray gas, which was detected with the Chandra X-ray telescope. And the blue emission that you see here is the radio emission. So this is some kind of a superimposition of all the different wavelength data together for this AGN. And so you see the radio, there is radio emission, but it's much smaller than the extent of the host galaxy itself. So these are known as radio quiet AGN now. And this is the majority of the AGN class. On the other hand, you see what are much more spectacular AGN in some sense, at least at radio frequencies, which is now called as a radio loud AGN. So here you see the blue light is the stellar light from the host galaxy. In this case, it's an elliptical galaxy. And the red emission that you see is, of course, it's false color, as you can imagine. This is only radio waves. And the extent of this is, of course, much larger than the host galaxy itself. It's, it goes to hundreds and thousands of megaparsecs, or rather thousands of kiloparsecs, or a few megaparsecs in extent. So the emission, these outflows, then kind of start, connecting between galaxies. I mean, that is the intergalactic distance which they cover. So the reason for these two kind of AGN is still a matter of debate. There's a lot of work going on to explain why only some sources seem to be this very powerful, whereas most of the sources seem to be these less powerful outflows. So this is known as the radio loud, radio quiet AGN divide, and there is a lot of work going on to explain why this is so. Also, after the initial work of Carl Seifert with much larger samples of sources which show these emission lines, it was found that there was primarily two types of spectra that were seen. One set of sources seem to show only narrow lines, as you can see here, and some sources seem to show a combination of narrow as well as broad lines, like the ones you see here, this broad base, especially here as well. So these are the same lines actually plotted for two different types of objects. So these are now called type 1 sources, which show broad lines as well as narrow lines, and type 2 sources, which show only narrow lines. Okay, so now I will come back to how we understand what we see in terms of spectra as well as the radio. But I want to use the next two slides to motivate you to, or rather to say why AGN are interesting and why should we study AGN. So AGN, there are several things which AGN can be, very, very interesting. Okay, let me start again. So AGN are the best probes of not only of this extreme gravitational physics happening in their own vicinity, but they can actually help you understand the universe through which the light travels. So this is kind of shown in this plot here. So you have a background quasar, because these quasars have these fantastic spectra, which we've seen earlier. Whenever there is intervening gas between the quasars and us, the spectra then starts getting dominated by absorption lines. And these absorption lines are happening due to either H1 clouds from galaxies, whatever. So all this line of sight emission is reflected, rather absorption is reflected in the spectra of the quasar. So you can study the spectra of these quasars, especially the ones which are at very high redshifts, and actually understand the H1 distribution, hydrogen distribution of the universe. So that's why AGN are interesting. And the second reason why AGN are very interesting is that they, even though the most of the action seems to be confined to much smaller scales in the center of the galaxies, they actually have much larger impacts. And this phenomenon is called as AGN feedback. So AGN feedback, there are several different ways at which this idea was arrived at, which includes the presence of cavities in the X-ray emission of galaxy clusters. As you can see here, this is the galaxy cluster Perseus. And Perseus A is the center of the galaxy cluster, and this is the Chandra image of this galaxy cluster. So this is all X-ray emission, and you start seeing a lot of holes here, which are known as X-ray cavities. So it's now believed that these X-ray cavities are actually due to the action of the active galactic nucleus in the center of these galaxy clusters, or rather the AGN in the brighter center galaxy of the galaxy cluster. So that is seen here in the right panel. So again, the blue emission here is the X-ray gas, hot X-ray gas. And you have these cavities. You can see this less density of X-ray emission in some regions. And when you superimpose the radio emission from these active galactic nuclei in the centers of these galaxies, you find that the radio emission seems to very neatly fit in these cavities. So it's believed that this X-ray gas is actually being pushed out by the radio jets that are being emitted from the AGN. Then there are other problems as well. There is something called the cooling flow problem, which is that even though this galaxy cluster is emitting so much X-ray gas, it somehow doesn't seem to be cooling enough to show emission lines. So something is keeping this hot X-ray gas hot. And it's believed that it's the AGN which is kind of keeping this X-ray environment very hot. So there are other ways as well, other indications as well, which come from galaxy luminosity functions. There is a close relation between the black hole mass and the galactic bulge. So somehow, even though the black hole itself is like tiny, it seems to impact the host galaxy. It seems to impact even the material outside the host galaxies. So that is why AGN are important, and it's the understanding of how AGN work and how they impact is kind of needed to understand cosmology. So now we come to this model of an AGN, which is now based on all the observational results that I presented earlier, which is the spectra and the radio emission, etc. So now this is kind of a cartoon to show what an AGN is. So and I think it's important to stress the fact that this is a cartoon because we don't have resolution to see the black hole accretion disk system at the wavelengths at which those regions emit. So that's important to keep in mind. It's a cartoon because we can't see it still. So there is a supermassive black hole, and I will tell about in the coming slides why we are very sure that there's a supermassive black hole in the center of these galaxies, which has masses of 1 million to a billion solar masses. And we believe that from the spectroscopic studies, the broad lines that we see are actually from gas clouds, which are moving very fast around this black hole accretion disk system. So because they're faster, they then give rise, because of Doppler widths, their Doppler widths are larger, so they give rise to the broad lines. And by broad, it means like several thousand kilometers per second velocity widths. Then the narrow lines are coming from these gas clouds, which are less dense, and they are moving slower. So they are the ones which give velocity widths of a few hundred kilometers per second, and that is what you see in the spectra. The density of these lines comes from the study of the presence of certain species and the absence of certain species, etc. So we have this whole constraint on the densities of these lines based on these spectroscopic observations. What is also interesting is that we believe that there is some kind of obscuration around this black hole accretion disk and broadline region. This is called the broadline region, which is kind of hiding the central engine in some, depending on how the AGN is oriented in the plane of in the sky. So if the AGN is oriented in such a way that this obscuration that hides your central engine, then you see only the narrow lines. And so you have a type 2 AGN. Whereas if your AGN in the sky is oriented in such a way that you can see through and see also the broadline region and the accretion disk, then you have a type 1 AGN. Now, again, here it's important to remember that it looks like a torus here. But we don't really know the shape of this obscuring structure. It could also just be a flared accretion disk on much larger scales. So there is a lot of uncertainty in the exact structure of these central structures of these AGN. But what is very clear, and that is where all the best resolution comes from, is at radio frequencies, that there are outflows which are launched from this accretion disk black hole system. And because of the technique of very long baseline interferometry, which I'll come to, we can see how very close to where these jets are launched. We can kind of go all the way till the black hole and see where the jets are launched. We also know one more thing, which is confirmed, is that the emission from this the radio jets, is synchrotron in origin. And that knowledge comes from the fact that it's a power law spectrum. It doesn't show any lines. It's a continuum spectrum, has a power law. It has a slope of 0.7, which is exactly what is kind of also expected for synchrotron emission from charged particles with a given energy index, which is usually 2.5. Also, the second thing is that the synchrotron emission is supposed to be highly linearly polarized, and that is actually observed. And according to theory, synchrotron emission should never be more than 75% linearly polarized, and that's also always observed. So we know this is synchrotron emission. Now let's come to the supermassive black hole itself. The proof of the supermassive black hole, I think now it's very clear. The most of the work that was done was based on actually our own galaxy, the Milky Way galaxy. And because the Milky Way galaxy the center of the Milky Way has been observed for 25 odd years, the stars which are individual stars which are orbiting the supermassive black hole in our own galaxy have actually now been traced to full orbits. So you know that, and so these are infrared studies which have been done with the Keck telescope. And complete orbits of stars which are moving around the supermassive black hole have been observed. And so from these very basic, calculations, if you just use the Newton's form of the Kepler's third law, you can find what the mass of the central object is based on the velocity of these stars and the radii. And so that turns out to be 4.5 10 to the 6 solar masses for our Milky Way. And of course, you all know that this work was awarded the Nobel Prize in 2020, and Reinhard Genzel and Andre Geges, who were involved in this study, were awarded the Nobel Prize. But now, of course, with the Event Horizon Telescope, we have actually kind of gone, all the way and seen the shadow of the supermassive black hole in our own galaxy. Okay, so I will come back to this towards the end of the talk. So the presence of a supermassive black hole is kind of now established. What is still a little bit unclear is how jets are formed. So there have been two, mechanisms which have been put forth to explain the formation of jets. One is the Blandford and Znayak mechanism, where the energy and angular momentum are electromagnetically extracted from the spinning black hole. And there you basically need to have a very strong colloidal magnetic fields already there around the black hole, or maybe anchored in the inner part of the accretion disk. And you need the black hole to be spinning very fast. So, so the power that you extract is the square of the magnetic field strength as well as the square of the angular velocity. The second model which has been put forth is known as the Blandford and Payne mechanism, where you are extracting energy and angular momentum from the rotating accretion disk itself. And it's believed that a combination of these two must be present in most AGN. And what is interesting to note is that the Event Horizon Telescope results of both Sagittarius A star, which is our own galaxy, and MET7, which is the first EHG result, they actually favor the Blandford and Znayak mechanism for the formation of jets. So now I'll come back to the question that we are trying to ask in this particular talk, and I want to present some results from our own work, which basically address this question: is why is there a divide between AGN of this sort, and why are some jets very large and most of the jets very small? So here, this is kind of quantified. This radio loud, radio quiet divide has been quantified by the work of several authors, including Kellerman, where basically what they found was that if you plot the flux density ratio of the radio at, let's say, 5 gigahertz, that's what they did for their study, and the optical light, then you see this, when you plot this for their sample, for a large sample, for example, they use the Palomar Bright Quasar survey, you see this bimodality. And this bimodality occurs at an R value of 10. So most of the AGNs seem to be in this R less than 10 region. These are known as the radio quiet AGNs. So it's almost 85% of them. And 15% or so were in the radio loud region, which is R greater than 10. Also the radio quiet AGN itself comprises of a couple of subclasses of AGN. I already mentioned Seaford galaxies. And much later, there was another class of AGN which was found called liners, which stands for low ionization nuclear emission line regions. But they're very similar in spectra. Spectral wise, they don't have very strong high ionization lines, but they're similar to the Seaford type 1 galaxies. So the radio quiet AGN comprise of these two types of galaxies. So mostly, at least in the low redshift universe, these are spiral galaxies with AGN. In the high redshift universe, most of these radio quiet AGN can be also found in elliptical galaxies. So the understanding is that these radio quiet AGN, because first of all, they're low luminosity itself, so they have low accretion rates. And because they have low accretion rates, the accretion disk is probably not similar to the radio loud objects. I mean, that is the belief. And so here is a cartoon to show what is believed to be happening in low luminosity AGN. So you have a thin disk, thin accretion disk, but then closer to the black hole, it seems to kind of become what is known as a radiatively inefficient accretion flow. And that happens because the accretion rate is very low. So when you have very low accretion rates, then the energy between the ions and the electrons cannot be shared through interaction. So basically, the ions kind of retain their energy, and the electrons are not able to lose any energy via this interaction. So therefore, all the energetic ions then get ejected directly into the black hole, and there is not much emission coming from the accretion disk itself. So it's a and the puffing up happens because it becomes very hot and it can't cool down. So so that is why we believe that there's this kind of an accretion structure in these radio quiet AGN. And here in the bottom is just to show what I've already shown you, one of the radio quiet AGN. This is just the radio contours of that same source to kind of highlight how it looks like. So you can see, you know, there is, it's complex, but you see kind of a bipolar outflow and maybe some kind of, you know, ends. It looks like what is known as a radio lobe, which seems to have a clear termination point, etc. So it's just to kind of show how it looks on small scales. And so to explain this, many suggestions have been put forth. There have been suggestions that the black hole masses and spins could be different in radio loud versus radio quiet. So they both are supposed to be smaller in the radio quiet AGN. Or it could be that the jet is somehow it's moving through a very dense medium. So it's interacting with this dense medium and it's losing its power. So that's why it's not able to go to much larger extents. So in order to test this idea, it's important to kind of start looking on scales where the black holes are, or rather the jets are just launched from the black holes. So that is where you need the technique of very long baseline interferometry. So what is very long baseline interferometry? So this is a cartoon to show what is happening. So you have radio telescopes which are not necessarily in one location, but you have radio telescopes spread across, you know, Earth. They could also be in space. And all you need to do is have the radio telescopes be sampling the same wavefront that's coming from your source of interest. In this particular case, it's a quasar. So as long as you can sample the same wavefront from these two telescopes, no matter how far they are, you are able to then kind of reconstruct the actual source intensity in the sky because of the technique of interferometry, radio interferometry. And because you can do these very large distances between telescopes, you kind of arbitrarily start increasing the resolution of your telescope. So in this case, the telescope actually is whatever the largest, so you need at least 3 telescopes to make an image. And whatever the largest separation is between these telescopes is the diameter of your synthesized telescope. And all this is possible because radio waves they have large wavelengths. And so it's easier to kind of compensate for any phase delays that happen due to, as the wavefront is going through the atmosphere. So this can, of course, also be done with optical waves, except that you need different electronics. And that is much more difficult to compensate for the phase delays, etc. For much shorter wavelength light. It's much more difficult technologically. It's easier to do at radio frequencies. So that's why we are able to create very high resolution radio telescopes, because the resolution is a function of wavelength and the diameter. In this case, the diameter is the largest separation between telescopes. So you can then end up having milli-arcsecond resolution. Whereas in a normal optical telescope, the resolution that we get is of the order of a few arc seconds. So you already get into milli-arcseconds. And then you, of course, if you can somehow make your wavelength even smaller, so you go to millimeter waves, and then you can even get higher resolution of micro-arcsecond. And so that is what the Event Horizon Telescope has done. So, so this is a picture to just show the power of VLBI. So on the top is the famous radio loud AGN called M87, Mercier 87. And it has these beautiful jets, lobes, etc. And when you look at this, or rather, when you look at this source with VLBI, you're sampling the very, very compact inner part of the jet itself, and then you're able to resolve it. So what was a point source in one of the radio telescope images is now actually not just a point source, it's a point source with a jet. And you can see very interesting details, which tells you about the physics of jets. Like, for example, when you do VLBI observations, you can see that the jet has these bright edges. And so, so there is seems to be some kind of a less intensity in the centers of images. And this has a lot of implications on how jets are launched, what kind of magnetic field structures are there, which produce these jets, etc. Similarly, so this is a very long baseline array. It's this set of 10 telescopes across the US, which work together like a VLBI array. And so that's VLBA. But if you can also use a set of telescopes which are working at millimeter waves, and that is what GMVA is, Global Millimeter VLBI Array. And so that has even higher resolution, because now you're going to shorter and shorter wavelengths. And so now you can kind of resolve even the core which was seen in VLBA can now be resolved into another core and jet. Again, you see this limb brightening. And then you can keep going further, and if you from 86 gigahertz, you now go to 230 gigahertz, and then you come to the Event Horizon Telescope. And so you're able to even resolve this part, which was the core there, and you see this image, which I think everybody is now familiar with. And this is this radio emission, we believe, is either coming from the accretion disk around the supermassive black hole, or it is the base of the jet which is launched from the supermassive black hole. And so these are some of the details. So this is now, I showed you the VLBA. This is the Event Horizon Telescope Array. And so these are the telescopes that were involved initially to produce the famous images. Now they're getting many more telescopes involved in this array to get even more sensitive high resolution images of other, maybe we can go further from the Milky Way and find black holes in other galaxies. So the resolution that we get for the previous work was from the Event Horizon Telescope. The first work was of the order of 50 micro-arcsecond. And so this is now the image of M87, and this is Sagittarius A star, which is the black hole in our own galaxy. So a couple of interesting things happen when you look at AGN with VLBI observations. First thing is that you find that the radio jets that you see, so these are just contour images of radio jets from some AGN. In this particular case, they are from the Mojave program. And Mojave is basically monitoring of jets of AGN with VLBI experiments. It's a sample of 150 odd bright AGN in the sky, which have been monitored with VLBI for several years, and every 6 months or so, 4 to 6 months, they are being monitored with VLBI. And so VLBI, so now this is the contours are just showing the radio emission. And you always end up seeing some kind of a bright point source here, which is called the core, and you have some kind of elongated emission, which is the jet. So you see core jet structures. And normally, when you go on VLBI scales, you don't see any emission from what is known as the counter jet. And the reason for this is that the emission, because this jet is just launched from the black hole, it's very fast. It's moving at the speeds close to speed of light, because of which if it has some very non-intuitive effects. One is that the emission from the jet which is approaching us gets Doppler boosted, whereas the emission which is from the jet going away from us gets Doppler dimmed. So in the jet frame itself, you have two jets coming out from the black hole, but in the observer frame, you end up seeing only one jet. Second thing that you see, which is also non-intuitive, is that the jet, so this is 3C279, it's another quasar. This is the core of the bright point source, which is stationary. And then you see the jet knots being, they're moving away over several years. And these jet knots seem to be moving at speeds greater than speed of light. So this is known as superluminal motion. And again, it's not obviously actually happening. It's some kind of a illusion, because these jets are moving fast, but less than speed of light, but they are oriented in some small angles, which kind of exaggerates this effect. And so basically, these are the set of equations that apply, which kind of explain what we see. So this is the relation I was, so let me go from the top. The observed luminosity is actually a function of intrinsic luminosity by Doppler factor. So the Doppler factor, Lorentz factors in beta, I think you're all familiar with from your classes of special theory of relativity. So the observed luminosity is much larger than the intrinsic luminosity, and that is based on the Doppler factor to the power 3. And also the spectral index of the synchrotron emission. The jet to counter jet intensity ratio is a function given like this. So depending on what the speed of the jet is and what its orientation is, this R value can be whatever. So you end up seeing one jet is much, much more powerful or brighter than the counter jet. This is from this relation. And this third relation is that the apparent speed of the jet is related to beta and theta this way. So sometimes even when beta is actually less than 1, which is speed of the jet with respect to speed of light is less than 1, depending on some orientations theta, your beta apparent can be greater than 1. So I just very quickly wanted to share some interesting results where we carried out these VLBI observations of a small sample of radio quiet AGN. So all the Mojave work is coming from these very powerful AGNs, powerful AGN called blazars. And VLBI studies of radio quiet AGN have not been done so far for very simple reasons. They are not as bright in the radio. And that makes it very difficult to, first of all, even detect them with VLBI. And to then, of course, if you don't detect them, of course, you can't monitor them at all. So those are the issues with carrying out VLBI observations of radio quiet AGN. But in the last several years, VLBI has got much more sensitive. And so now you are able to at least look at some of these radio quiet AGN. So the telescopes are now able to detect some emission from these very weak radio quiet objects. So the sources we looked at belong to a particular sample called KISS-R, which is Kitt Peak National Observatory Internal Spectroscopic Survey. And so this we chose these galaxies, a few galaxies, which showed a peculiar spectrum. So this is the optical spectrum showing the H alpha line. And we found that the lines seem to have double peaks, as you can see here. So these two blue components are the fitted components to the actual observed lines. So we found, we took a small subsample from this large sample, which showed these peculiarities in the spectra. And we also made sure that they were already detected, these sources were detected by some radio surveys like the FIRST. It's a all-sky Northern Hemisphere survey with a very large array telescope. And so we needed this before we could do VLBI, because you don't want to, if you don't know if they're detected at all from, even larger telescopes, then it's very unlikely that they will be detected with VLBI. Now, why were these sources interesting? Because of these double peak lines, they could be candidates for binary black holes. And why is that? So the idea there is that each of the black holes has a narrow line region associated with it, like I showed you in the model in the previous slides. And when you have two black holes, then you have two sets of narrow lines, and that's why you get these double peaks. But another way to explain this is that somehow if you have two jets going in opposite directions and they're pushing the narrow line clouds in two opposite directions, so one of them is blue shifted and one is red shifted, then you could also create these double peak lines. So this is just to show the sample. The color is the optical images, and the green contours are showing the radio emission. And so the VLA FIRST survey detects all these radio sources, and they're point-like. They're not very interesting to look at in the radio. It's not like those beautiful, lovely jets which go, beyond the host galaxy. You just see point sources. But when you look at them with VLBI, you start seeing jets. So that was a very interesting thing that we found. We did not expect to see that there would be so many jets in these very weak radio quiet AGN. And so this is one of the sources. And what we could do is, like, we use those relations that I showed you earlier to kind of look at the intensity ratios of what we think is the jet which is approaching us versus the jet which is going away from us. And that kind of gives you a limit on beta and theta. And then you have to then assume a theta to try to get some idea of beta. And the theta we assumed comes from the fact that these are type 2 Seyfert galaxies, or type 2 radio quiet AGN. And those are the ones which have narrow lines. And so the narrow lines, if you remember the AGN model that I had shown you, are the ones where you don't see the broadline region because of the torus. And this torus has some kind of an opening angle, which is supposed to be around 50 degrees. That comes from different observations. And so if you assume that the angle is around 50 degrees, then you kind of get an idea of the jet speed. So that is what we did for these sources. And those jet speeds seem to be high. This is another source from the sample. So the jet speeds that we derive are in this range, 0.003, that's small, to 0.75 C, but of course always less than 1 C. So that was interesting. But very recently, we actually were able to get a second epoch image of these sources. And one of them, this is one of them shown here, seems to show a jet speed which is superluminal. So this is now actual measurement. That the previous one was the limit derived from just the image itself. This is an actual measurement of jet motion, and it seems to be superluminal. So that was very interesting, and this is keeping with the idea that jets can be fast in radio quiet AGN. So finally, this one more source which I wanted to mention quickly is we thought when we got the first epoch data, it looked in the radio image, it looked like 2-point sources, which would be consistent with the binary black hole on parsec scales. But as it turns out, the second epoch observations shows motion in one of those components. And then again, the motion suggests some kind of a speed which is superluminal. So that's very interesting. So it looks like even this particular source, which we thought could have been a binary black hole candidate, actually is a core jet structure, which is also moving very fast. So the main result from this work was radio quiet agents seem to have fast jets. So why is this important? This is important because if you remember the ideas which have been put forth to explain radio quiet, radio loud objects, one of them is that there is a difference in the black hole spins, and so you should have faster jets in radio loud AGN versus radio quiet, and things like that. So this has implications on all those ideas. The second thing is that we now believe that this double peak lines that are coming are not due to binary black holes. That is not, otherwise we would have seen some signatures in the VLBI images. Rather, it is the jet which is pushing out the narrow line gas clouds and giving rise to the double peaks. So then there are two things here now. So first is that there could be fast jets in radio quiet AGN, and somehow these fast jets also seem to influence the material around their host galaxies. Okay, so those are two very interesting results. Obviously, they have to be, we need many more data to kind of put this on a good footing, firm footing. So I want to end my talk with two interesting examples, which then kind of bring out another side of these radio quiet AGN. So I showed you these what look like very boring, point sources in the radio kind of AGN, radio quiet AGN, seem to have jets which seem to be fast on small scales, just as they launched from the black holes. The second interesting thing that has been seen for some of these AGN is that the radio emission seems to be happening in bursts. And so this is an example of another radio quiet AGN called Markarian 6. So this grayscale emission that you see, which looks kind of flimsy, very low surface brightness emission. So this is of the order of like a few kiloparsecs. The size of this whole radio source is still much smaller than the host galaxy itself. So it's still within the host galaxy, even though this is definitely a larger jet compared to the Kisser sources that I showed you before. But what is interesting is that when this radio source is looked at multiple resolutions, it seems to show additional lobe-like structures. So when you go look at the center of this source at a higher resolution image, you see another set of lobes. And then when you see that lobe with another high resolution image, you see another set of jet kind of structure. So there is like a structure within a structure within a structure. So that is very interesting. Which has been now seen in a couple of AGN, but still a handful. So I want to show this particular source, which is we just got these results, and of course, Namrita is part of this work as well. So this is another AGN which seems to show this structure within a structure. So this is a lobe-like image, rather lobe-like structure that was observed in this particular radio quiet AGN called NGC 2639. And so these contours are radio emission, and this particular image comes from the Giant Meter Wave Radio Telescope, GMRT, which is run by NCRA. And this high resolution, if you take a high resolution image and examine the core of this structure, you find that there is another set of lobes in a completely different direction. So this is a smaller set of lobes. And then a high resolution image of this radio structure reveals another outflow-like emission in a completely different direction. And then a very high resolution, very long baseline array image, VLBI image, shows a core jet structure in this direction. So you see, when you look at just the radio emission of a radio quiet AGN on different spatial scales with different telescopes, which have different resolutions, then you start seeing structures in different directions. Very similar to the one that I showed in the previous slide. So it looks like even though these AGN are tiny and they stay within the host galaxy themselves, the fact that they can have these different orientations in the radio outflows does seem to have some impact on the host galaxy themselves. And so this is definitely seen in this one source where, so now I just wanted to also show this image here. So here, the blue-green image is the optical light from the galaxy. So you see the disk. This is the disk of the galaxy. This is the GMRT lobe that we see. And this is the red thing is the VLA lobe that I showed in the previous slide. This galaxy also seems to have a hole in the CO molecular gas. So it looks like this radio emission seems to be doing something to the molecular gas. It seems to be pushing some gas around in the host galaxy. And these are UV images of the same galaxy, which seems to suggest that there is also some differences in star formation in the host galaxy. So this definitely seems to be a signature of a radio quiet AGN having some kind of feedback effects on its host galaxy. And so by feedback effects here, it's kind of either pushing out gas, which will then slow accretion, Also, the gas, the radio jets could also be kind of compressing some gas, which would then increase stuff emission. So this is basically a cycle of both positive and negative feedback, where the AGN is either suppressing or igniting stuff emission. So all these activities are happening in the centers of these radio-quiet AGN. So the AGN feedback could be from this episodic activity, or it could also be the cause of the episodic activity, because when you're pushing gas out, you're stopping accretion, and then it takes a while for the gas to accrete again, and maybe it is then giving rise to these new jet lobes. So it's a very complex, self-contained process. So let me now summarize all my many slides, and I hope it was not too much information, but I'll be happy to address this in the question answer session. Majority of the AGN are radio quiet, and the origin of this radio quietness is not clear. When you look at these radio quiet AGN with VLBI, where you are actually trying to now look at jets as they launch from supermassive black holes, this kind of monitoring has been done only for the AGN which have large jets. They have not been carried out for small scale jets. And when you do, it seems like these jets are just as interesting as the radio loud sources, and seem to be also impacting the gas clouds around them. So therefore, jets in these even radio quiet AGNs seem to be influencing their environments and causing AGN feedback. So before I end, I just wanted to show a picture of the telescope that we operate at NCRA, the Giant Meter Wave Radio Telescope, and some new results which are coming out from GMRT with respect to VLBI. So we just last year did a VLBI experiment where we used telescopes in Europe and the GMRT to create high resolution images of this particular blazar. This is a gamma ray blazar 3C454.3. So this is the radio image of the blazar without GMRT, and this is the radio image of the blazar with GMRT in the VLBI array. So this was just like a test experiment, and we are able to see more details now. What looked like a core now looks like a core jet structure. So we are looking forward to more exciting times and much more, VLBI studies in the near future. Okay, thank you. I'm happy to take questions.
Thank you, Preeti, for a very nice talk on AGNs. Before opening the floor for questions, I would just remind everyone that please stay until the end, so that we can take a picture before leaving. And then now anyone can ask questions to Preeti. Yes, Namrata.
Hi, Preeti. Really nice talk. So I was wondering, like, with your VLBI observations, have you seen any difference in the jet structures between type 1 AGNs and type 2 AGNs?
That's a good question. So for our own work, of course, we actually weren't looking at type 1, type 2. So all our sources were type 2. But there has been a lot of work done on type 1 versus type 2. So for example, there is this work by Dharamveer Lal and Alan Roy. There's a lot of initial work that was done, and I think there were initially some suggestions that one type of jets was smaller in extent than the other, but I think that has, with more data, I don't think there is a huge difference between type 1s and type 2s. I mean, initially there seemed to be, but I think that's with more sources, I don't think there is a huge difference coming out in the structures.
Moushami.
Hi, Preeti. Great talk.
Nice
to see you. Yeah,
nice to see you.
So, Preeti, I had a question. On VLBI scales, you see a lot of change in the direction of the jet, right? But you
Yes.
don't see that in the large jets.
Yes.
Is that telling us something about the mechanism for the large jets versus the small jets?
Yeah, so that's a very interesting question, and I think that is it's a good way to explain what we see with VLBI. So VLBI is because you have these telescopes which are far flung, and you kind of creating a synthesized telescope which is from these telescopes which are very far from each other. So we don't have what are known as short spacings. So that means you don't have telescopes in between these large separated telescopes, and so you're missing all this emission from the diffuse emission between in the radio jets. So what you see are just the bright compact portions of the jet. But what we believe the jet is actually much more. It's like a broader flow around the VLBI structures. So what you see as changes in the VLBI jet direction are probably changes which are within, bright components or shocks within this larger outflow. And so the larger outflow may be still, decided based on the black hole spinning direction, whatever accretion disk. But the smaller structure is just kind of, going into the details of these individual jet blobs. So yeah, they can both be there at the same time.
Okay. So it's because we're missing the diffuse structure. Probably.
Yeah.
Okay. Thanks.
Shweta, can unmute.
Hi. Should I stop the video? Is it important? Wait a second. Sorry. Okay. So, I just wanted to ask a question regarding is it the slide before this, wherein you showed the when you talked about the feedback.
Yeah.
Yeah, I think that one. So I was wondering if I mean about what you said about the jet feedback, probably well, it's not encouraging, but feeding or increasing the starburst or star formation rates.
Yes.
Because I would think it would be a bit more opposite, right? Because it would heat up the gas, which would create a very unhappy environment for star formation.
Yes.
And I was wondering if such features would also, I mean, such phenomenon would also probably show features in X-ray.
Yes. So that's excellent. You're right that I think when the gas is moved out, it would kind of decrease star formation. But what is also seen, which I haven't shown in this image, even for this particular source, which is like a radio quiet AGN, there seems to be much more dispersion in the gas around the jet, edges of this jet. So somehow the jet also, while it's pushing out some gas, it's also compressing gas in certain directions. And when that compression happens, then that could lead to star formation. So both positive and negative feedback seems to, is happening at the same time in these kind of sources. So it's a complex, interplay between the jet and the medium. Okay. X-ray signatures have been looked at, and I think they have actually been found as well. Like Markarian 6 itself, we had done some X-ray observations to see if there was some impact of these jets. So the shocks were not very pronounced as they are in, for example, Centaurus A, like the very bright radio AGN. But there are some signatures of small shocks happening because of these these weak outflows. So X-ray signatures are also there. So to answer your question, what is expected is also seen.
Okay. Also, thank you for the talk. Actually, it was really nice. I just have one more question. Can I do that, or does somebody?
Go ahead.
Okay. So I was wondering from this. I mean, of course, we don't have a very big sample size, but when it comes to low luminosity AGN, we don't have a very big sample size for a lot of things.
Yes.
So to understand whether the thickness of the let's say where the density of gas or dust, considering that the torus is sort of puffed up when it comes to a lot of these sources,
yes,
is the reason that we probably the jets, the smaller underpowered jets, are obscured. How could we probably do that?
Okay. Right.
Because,
sorry. Yeah, go ahead. Sorry.
No, sorry. I mean, the thing is, I mostly work with 3HE side of everything. So my knowledge when it comes to optical and radio is slightly shaky. So I apologize for that.
No, it's perfectly, it's a good question. And so radio, the thing about radio waves is, of course, that there is it's difficult to completely absorb radio emission. So you do see, even if there is dust, the radio emission kind of shines through. So you can see, in fact, I mean, there is a lot of dust in these galaxies, but you see all the radio emission anyway. When you're talking about so the torus kind of doesn't stop in the imaging of the radio emission itself behind the torus. But everything else in the optical light, of course, is obscured. So you won't see any of the continuum emission from the accretion disk, and you won't see the emission from the clouds, which are giving the lines. So, but the radio emission shines through.
But that would create stunning shocks, would that, as it interacts with torus, or would it not?
Okay. So there, the idea is that the radio jets are kind of launched perpendicular to the accretion disks, and it's very likely, though there are a lot of interesting results coming out from these integrated field unit observations with Gemini and other instruments. But normally the jet is launched perpendicular to the accretion disk and the torus. So then it doesn't interact. It doesn't really interact with the torus unless there is a new jet which is born and somehow there was a torus from previous activity or something, and then the jet kind of goes through the torus. In which case, I mean, it's still I think not dense enough to, maybe in some AGN there is, but it's probably not dense enough to kind of stop the jet from expanding further. But yeah, I think there are different AGN which have different, which show different observational results.
Yeah, because I thought with VHE it obscures pretty well with gamma emission.
Right.
So,
I see. Okay. So what AGN are we talking about? Like these are some Compton-thick AGN?
Yeah, I mean, okay. So the thing is, when I'm trying to ask is if even within low luminosity AGNs,
yes,
there are AGNs with higher star formation. So if we have to disentangle something from jet and the shocks created by, for example, a star burst nucleus.
Okay. Right. So this is a very interesting, I mean, this is a problem for radio quiet AGN for sure. Like some of the radio emission could actually be coming from starbursts. And so what we did, like especially when you go to kiloparsec scales or hundreds of parsec scales, the radio emission could actually be coming from some supernova winds along with the AGN jet and wind itself. So it's much more complex. But when we start going to smaller scales like VLBI, I think most of the there is not much stellar emission, as you can see. I mean, the radio structures themselves look much more, jet-like. You don't have that many, that much diffuse emission on those scales. And that is, of course, also because of VLBI. So it's true that on larger scales, everything gets mixed for radio quiet AGN.
Thank you.
Manami.
Yeah, so I was wondering if, I mean, jets are a good place for cosmic ray acceleration. So do you see any kind of gamma ray emission from exactly the regions of like radio contour or X-ray emission?
Right. Yeah, so they are exactly, I mean, the first neutrino, extragalactic neutrino is associated with the blazar jet. And it is believed that even the radio quiet AGN, in fact, I think interestingly, what Fermi, the Gamma Ray Telescope found was that there's a large fraction of AGN that were detected at Fermi gamma rays were actually radio quiet AGN. So even though these are like, they look like they have very, small jets, etc., they somehow are producing this very high energy emission. And so that has to do with the composition of this outflow and the energetics of it. And so, but we can't, of course, we don't have enough resolution in either gamma rays or neutrinos to actually directly associate with some jet features, or so that we can't do that one to one. But it is expected that these jets are producing high energy photons.
Okay, thank you.
Yeah.
Can I just ask a question related to that?
Yes.
So there have been only 2 neutrino detections. One
Yes.
is from NGC 1068, and the
1068,
other one
yes.
is a Blazar
Yes.
TXS something.
Yes, yes.
Right. So do you have any thoughts on that? Like I've been thinking about this. What is so great about 1068 that it's giving us a
Exactly.
neutrino?
Yes, I think that's an excellent, we don't know, and we don't know what exactly is producing those neutrinos either. So people assume already always a fast jet, but I mean, would that could mean that some of these radio quiet AGN are also fast jets, but the exact physics we don't know. But it is interesting. I don't know why 1068 is interesting. That's a good question.
Yeah, I found that very puzzling.
Yes, it is puzzling.
Yeah, it is at liner though, right?
1068 I don't know actually. It could be
Is
a
it a
liner.
liner? No.
It could
Because
be.
does it have the RIAF? That, what's it called? That radial?
RIAF?
RIAF.
For 1068, I'm not sure if for
Okay.
1068 specifically what is I thought it was one of the first CFERs that were
Oh, okay.
always observed. I mean, I don't know, but I really don't know much, so
Okay.
I
No,
need to look
that's
that up.
okay. Yeah.
Suma?
Hello, Preeti.
Hi, Suma.
First of all, thanks for showing the GMRT EVN images. It's always nice to look at them again. So,
Yes.
my question is also regarding the source that we are seeing on the slide here. I mean,
Yes.
maybe you mentioned this, but I missed. So I was, from what I could imagine, to create such cavities at galactic scales, you would probably need slightly powerful outflows and jets. So, and this clearly there are cavities that you would see, if from large jets. So I was wondering if this was a radio loud source, which has now slowly faded and has become a radio quiet source. So you see these cavities on large scales, but you see a radio quiet source in the nuclear region because the large scale emission has now started fading. Could it be some kind of an evolution of that sort?
That's a great question. So, I mean, we do believe, I mean, based on many things, that this AGN activity could be episodic. I mean, and also some sources which were radio loud ones may be now radio silent, for example. There are some systematic differences between radio loud, radio quiet objects in the sense like, most of the radio powerful ones are not in spiral galaxies or disk galaxies, but there have been some exceptions for that also. So in principle, that idea is there. But I think more importantly, it's important to remember that we don't understand the outflow itself. So we don't know when we actually just looked at the radio luminosity of this particular source and estimated the kinetic power based on just radio luminosity and some empirical relations, that exist for radio loud AGN, for example, the kinetic energy turned out to be very high. So the kinetic energy of these from the radio luminosity itself are actually comparable to the Fanarov-Riley type 1 radio galaxies. So they're not that small. So you only need very little of that to kind of create a cavity. So we did some calculations in the paper, and we just needed like less than 1% of that could create that cavity. But the question is like, what we are seeing is the synchrotron plasma, but the outflow itself could be a mixture of that with something else as well. So yeah, it's a little bit like, it's a puzzle. We really don't know. But if you just went from radio luminosity to kinetic power, they seem to have the kinetic power.
Yeah, thank you.
Is it easy to connect, like you showed many lobes coming out? Is it easy to
Yes.
connect the launching frequency or timescale with accretion timescale?
Yes, yes. So that we did actually for this. This is one thing which was very interesting for the source is that we could kind of constrain the lifetimes for each of these episodes based on because we had multi-frequency data, we could do a spectral aging. And so we actually found that the spectral ages were like this. So it was like 34 mega years for the largest structure, then 12 mega years for the smaller one, and 3 mega years for the smaller lobes. And so it seemed like the source seemed to be kind of restarting every 10 million years from this particular thing. And that timescale is also very interesting because that is the timescale also for the expected minor merger rate. So every 10 million years, there could be a minor merger, then which kind of gives rise to each of these different episodes. So we could get some ages, and they seem to match other things, but they could be unrelated to the minor merger completely also. But that is the number that we got.
Also, in your cartoon of like broad line region, narrow line region, what are the different length scales of like within the galaxy or outside the galactic and like the
You're talking about
going
the
into the
AGN model
circumgalaxy?
itself?
Yeah, like in
Right. So yes. So this I'll tell you. Yeah. So
yeah,
this
this
yeah. So these the broadline clouds themselves are of the order of a parsec or so, or maybe a few parsec. I mean, that is the kind of extent we're talking about here. This is now going to tens of parsecs to hundreds of parsecs, the narrow line region. But this is like parsec, sub-parsec scale, the inside part, the broad line and the accretion test system. And the torus itself, like, which has not really been, I mean, there have been claims that this torus structure has been imaged, but the ones that have been imaged with the VLTI observations, those are of the order of a few parsec, but they may be larger and the actual tori may be smaller, so we don't know. But those are the extents we're talking about, like parsec scale for the central part and hundreds of parsecs for the narrow line region clouds.
Thank you. There is one more question. Veena, can you please unmute?
Yeah, thanks for this nice talk. So my question is for the AGNs, the spectral energy distribution across the entire electromagnetic spectrum, where does it peak? This is one question. And secondly, if you compare the radio loud and radio quiet, is the SED of radio loud a scaled up version of radio quiet, or do you see any shift in peak or anything like that?
Right. So for the sources that we've studied specifically, we haven't really created a broadband SED, but it's known for much larger samples of AGN that at least the shapes of the SEDs are similar between radio loud and radio quiet, except the radio end itself. Like most of the emission seems to be for the radio loud AGN at least seems to be in the blue optical light. So that is a big blue bump. Some of these low-luminosity AGN have what is known as a red big bump, which is like centered. The peak seems to be shifted toward the red longer wavelengths. But the shapes are not very different. And in terms of, for our sources, we haven't compared, but I think it's a good question to see if they're scaled up versions. I think they, right. I think they may be scaled up versions, but not by a huge factor. Because I think in terms of optical light, there's not that much difference between very radio quiet and very radio loud objects. It's in the radio frequencies where the difference is, rather than at other frequencies.
Okay. And are there any gamma ray detections of this?
Yeah, so not specifically individual objects, but like I said, surprisingly, when gamma ray telescopes looked at the sky, a large fraction of the detections were actually radio quiet AGN. So they happened to be narrow line Cepheid-1 galaxies, etc. But they were surprisingly, there were a lot of Cepheid galaxies there.
Thank you.
Anyone has any more questions?
Can I ask a question?
Yeah.
Huh?
Go ahead, Moshe.
So Preeti, in the second or third slide, you talked about the two jet launching mechanisms. I think one is Blanford-Zanuck and one Blanford-Payne, right? The two.
Yes. Yes.
So do you think, the first question is, do you think your VLBI observations, and even if we go to millimeter VLBI, do you think you'll be able to distinguish between the two? And do jets arise from the inner edge of the accretion disk, as someone told me? I think Heino Falke told me. And because I thought, you can also get, a little bit jets from the winds coming from the accretion disk. So I have this confusion, these two questions.
Yes. I think I've not been following the EHG results very closely, but actually the EHG results are kind of pointing to the Blanford-Zanuck mechanism working to explain their images. And I think it seems to work both in MET7, which is radio loud, and Sagittarius A star, which is radio quiet or radio silent. It seems to be working in both cases. And also the other thing they're finding is that it's all consistent with the magnetically arrested disk, or MADS. They seem to be, so basically, it's kind of the Blanford-Zanuck mechanism where you just have an increase in the magnetic flux around the central part of the accretion disk from this material which is inflowing. And that is needed to kind of produce jets, but that is present both in MET7 and Sagittarius A star. So I think that's all those things. We are kind of in the early stages. There's a lot of modeling happening still to explain the EHG results, EHT, total intensity, polarization results. But so far, it looks like, first of all, the answer to the question is yes. It can be. I think we should be able to soon, settle on, the best mechanism for producing jets. For Blanford-Payne, I think when you're talking about larger scales than that are being probed by EHT in some sense, right? Like, because you're coming very, very close to the black hole. I think to study those scales, you probably have to go a little further.
So do you think that the jets are coming from the inner edge of the accretion disk, or they can come from various places?
Yeah, I think it's not clear, no? I think it's not clear where they're coming from.
Yeah. He was very certain about it, so that's why I had that question.
Right. He thinks it's coming from the inner part of the accretion disk?
Yes. This was many years ago, but I think different people have different views, so I just was wondering. So it's not certain, I guess, right? It's not certain.
I think there is some ambiguity, as far as I remember. I mean, the MET7 itself, they are trying to go from the EHG scales to slightly larger scales to see an actual jet connection. And I think some results have come out which kind of show, so what you see in the EHG result image is maybe the base of, in which case you can kind of constrain where it is coming from, because you actually have sizes, actual sizes, and that may be the inner accretion disk. So that may be coming from the inner accretion disk, which would be consistent with what Heino Falke said.
Okay. Thanks, Preeti.
Yes.
Shrishti, can you please unmute?
Hello, ma'am. I had a question regarding variability. How does variability compare for radio loud and radio quiet AGNs? Also, are there specific time scales where we can look out for the same? And again, how do these time scales differ for radio loud and radio quiet AGNs?
Right. So variability, I think you have to specify which wavelength we're talking about, because variability, depending on which wavelength we're talking about, comes from different structures in these AGN. So, for example, optical variability could be coming from some activity happening on the accretion disk itself. Radio variability could be the presence of shocks in the jet. So it depends on, what exactly we're talking about. And the variability, apart from where it's coming from, it's also what is producing it. So like shocks versus, some energetic events on the accretion disk. So I think, I'm not sure if there is any systematic difference between variability But yeah, I think we have to specify what exactly we're talking about, which wavelength.
If we take the case of radio wavelength like chalk, then what would be the?
I think if you just took the radio wavelength, and so if you just monitored, yeah, okay. So if you monitored, for example, blazars, which are like, these very radio powerful AGN, if you monitor those, they seem to be highly variable, much more so than maybe other radio classes. And that is because their jets are kind of pointing towards us. So all effects are amplified in some sense, like everything, the time scale appears to be shorter than what it is actually in the jet frame. So that is more a relativistic effect because the jet is kind of pointing towards us rather than anything intrinsic. So it's an orientation thing rather than, anything intrinsic.
Okay, I think we are anyway almost past the hour by 30 minutes. It's such a popular talk. And so I think we can stop here. And before leaving, we should take a picture. So I'll request everyone to come in the video. Who's clicking? Samskriti, are you clicking?
Yeah, I can take it. Yep, done. Yeah, thank you, Preeti, for the great talk and all these very interesting questions from very different perspectives. So, yeah.
Thank you. Thank you for inviting me.
Thanks, Preeti, and thanks everyone for organizing this talk. It was really good. I'm sorry I missed the first one. Yeah.
Yeah.
Yeah, we'll have
Thank
many
you.
more, and we have already the next 2 to 3 speakers already booked. So,
Okay.
yeah,
Lined up. Yeah.
more exciting talks coming up.
Okay. So can we give the link to other people if they're not members of Karina's? Can we pass on the link?
Yes, yes.
Sure.
I mean, we share a registration link typically on Twitter.
Okay.
And then we finally 1 or 2 days before the talk, we give it to all the registered participants.
Okay.
Yes, you can share with everyone.
Okay. So even if someone has forgotten to register just before the talk, I can just share it with them?
Yes, yes.
Yeah,
I
yeah.
think we have a reasonable capacity right now, probably 100.
Okay. Okay,
Yes.
great.
Okay.
Yeah.
Okay, good.
Okay.
Good.
Thank you so much.
Thank
Yeah.
you so much.
It was
Bye.
great seeing you all.
Thanks.
Bye.
Bye.
Yeah, nice to see you.
Thanks
Yeah.
for the talk.
Bye.